So up next, ladies and gentlemen, we have one more excellent session on the topic Neuro Symbolic AI by Professor K.V. Subrahmanyam, sir, of CMI. Professor Subrahmanyam is a professor at Chennai Mathematical Institute and has been at CMI since 1994. His main research interests include geometric complexity theory, that is GCT, quantum computing. He also works in AI ML and teaches courses in ML as well. Optimization and quantum computing is the core. So may we request sir to please take over this session, please sir.
So thanks to the organizers, Suchitra, Sukumar, the entire gang for asking me to speak on this. Well, it has taken me some effort because I had to read up all of this. Yeah. Okay, so I'm going to jump into, what is this? Point there. Okay. So before we start, so I'll quickly take you through the problems that the old sort of vision models had. So these are sort of classical problems. I suppose all of you know it. But nevertheless, these are problems that still exist, and therefore the motivation was to tell you that these kind of problems were there and they continue to be there even with the current set of models. So, so this is the classical picture of training a vision model to recognize sort of animals. And so on the right side of the screen, you can see a panda, and the model says that it is a panda with fairly good confidence. And what happens is that you add certain noise to the model, and then you get this, the image of the panda, which is on the right there. The model certainly says that this is really not a panda, this is a gibbon. Now it says it, and to us it is absolutely clear that what is there on the right is very similar to what is there on the left. But nevertheless, the model has gone haywire and it has declared that what it sees is actually a gibbon when it was doing panda quite well. So these are sort of perturbations that you can add. These are called adversarial perturbations. There is a theory behind how you generate these perturbations. And basically it really tells you that very small, visually meaningless changes could cause really large semantic errors in vision models. Yeah? And the conclusion that you would draw from this is what I have written in the right side bottom, saying that really purely statistical models are probably not robust. Adversarial noise could really fool them. Yeah. So there is yet another setting where these vision models really fail. So on the right, you will see a ship. A model, a data set called CFAR has that particular image. So one could, you could train sort of vision models to do really well on CFAR. And it would, of course, make no mistake on that ship that you see by itself on the top there. But what people observed was that removing from the training set the bottom 9 images of ships that you see. Now, CFAR is a database which has close to 100,000, I think, images, of which I think at least 1,000 of them are actually ships. Now, you remove only these 9 images, and the vision model suddenly sort of, which was observing that ship, which was classifying that object, that image as a ship with almost 95% accuracy, you remove these 9 9 images from the training set, and the ship classification accuracy dropped down to 10%. So what this shows is that the performance of your model on certain images could really depend on a very small subset of your training sample. Now remove those things from your training samples and your model could go for a toss. So these are all sort of indications that, well, you may achieve really good accuracy on models, but what exactly is the reason why your model is doing what it is doing? This is something that needs to be understood. Yeah? This is just a sort of pointer to these facts. Yeah? So it also points to really the, so there are other reasons why mere image recognition is not sufficient. For example, I could give, well, this doesn't really look like an image, but suppose I input that particular image, and I give it to a vision model. Well, a vision model could be trained very well to recognize the digits that are present on the image. It could recognize 3, it could recognize 4, it could recognize a plus there, it could recognize a 9 and an equal to. So vision models can be really trained to do that really well. But to ask a vision model to check whether 3 plus 4 equal to 9 is correct or wrong is not something the vision models can actually do. Because while they are good at actually perceiving the digits, what they are not good as is checking the arithmetic that you want them to infer on the image. That is something very hard. Neural image classifiers can actually recognize digits. There is no problem. It can output good class labels. Everything they can do really well. But at the end of the day, pattern recognition is not reasoning. If you give that particular image to a vision model and ask it whether this is a valid sort of this is a valid expression, this is not something vision models can actually do. And this was the state till about 2020. And then somewhere in 2017, when people discovered transformers as an architecture, and so these are all things we're familiar with, but nevertheless, I thought I should take you through this journey because vision models came first, and then people actually developed sort of language models. So this was the sort of this is the history of these language models. The discovery of transformers in 2017. Then between 2018 and 2020, so this was described to us by Manish Gupta in yesterday's talk. The BERT models came where you really masked certain pieces of the input and asked the model to predict what those masked pieces were given the context. So this is how language models began to be trained. And of course, in 2021, between 2021 and 2023, we had these wonderful foundation models. So soon after COVID was when all of us sort of woke up to the fact that GPT is there and GPT does really well. And this is the emergence of these foundation models, which are single models which can do multiple tasks. Yeah, and this is something that people adopted really quickly. Yeah, they could do a bunch of really, really good tasks. Yeah, but the core problems of these models are the following. These are all, again, core problems that all of us are familiar with. Hallucinations is one thing. Then the other thing is that these models are still susceptible to adversarial attacks. So prompts of certain kinds can cause these models to sort of, yield answers which you would probably not want. Then there is really no way to guarantee that the model does not answer in a particular way. This is not something that we yet understand how to do. And of course, the big problem is one of limited explainability. But nevertheless, the big problem is that people actually went ahead and adopted these models, and this is a cause for concern. Yeah? GenAI was deployed very rapidly. In the last 2 years, we have seen a lot of deployment. But of course, as in the first talk showed us, that while there has been adoption, there has probably not been scalability. That's a different matter. But now people are back to questioning these models. And now the question is whether the concerns really are whether the concerns are that the model should be trustworthy, the model should be safe, and correctness of the model is something that is of paramount requirement. Yeah? Whether we can actually develop these models, use these models so that they are trustworthy, so that they are safe, and so that they do correctly what they are supposed to do. And this leads us to the question of whether these models, while these models are good at learning, is learning itself sufficient? And what the answer to that is really no, because there have been some industry wake-up calls, which, again, all of you are familiar with. For example, there is this fintech company, Klarna, which reduced its staff by 22% in 2023, but this year they announced that they are rehiring. And one of the reasons they are doing this is because customer expectations. So they replaced some 22% of their staff with AI, and they are doing customer support. This is a fintech industry. But then they found that customer expectations, customers came back to them with complaints. Now, this has caused them to once again look at replacing the AI that they had embraced rather easily with, again, human expertise. Salesforce is another company which, again, last year, actually, they announced in a big way that they are going to sort of replace a large number of their employees. And I think they cut down their employee base by around 22% or 23% again. But in fact, recently in a there was a talk by, I forget the name of this lady. So she actually says that they had more faith in AI last year than they have this year. Yeah, and what they have actually announced is that they are going to shift towards not automation by LLMs, but to deterministic, what they call deterministic automation. So these are all sort of wake-up calls which should tell us that while these models are really good, there is something that they lack, and this is something we would like to understand. We want to make these models trustworthy, we want to make them safe, and we want to have certain guarantees of performance. Yeah? So what is being offered? Okay, so these are the strengths of these models. So the real limitations that we need to stare at. Yeah? The limitations are of the following. So the first one, all of us are familiar with, that if you are given data which is out of the distribution from which the model has been trained, there is a problem. The model could actually screw up. One big problem is, of course, the fact that this is a black box that is provided to you. So now you train this model, you give this model. Now this is a monolith. I need to use it the way it has been trained. Now there are two problems with this. One which I think Seth mentioned in his talk yesterday, which is that these models keep getting trained. So while you may have used a model which was trained yesterday, and you may have used it in your application, tomorrow the model has been retrained, and maybe there are certain things that the model will not do the way it was doing it yesterday. So this is something that was alluded to yesterday, saying that suddenly there might be certain laws that are put in place, and the model cannot now sort of go and access certain amounts of data. So then the model goes for a toss. So that is a big problem with these monolith applications that you have. They are not pluggable. They are not easily pluggable to everything. They are not modular. This is the big problem with these large LLMs. Then what they certainly lack is robust planning. When there are multiple probable ways of deciding, it's not clear how the model is not really good at deciding which of these routes to take to reach to the decision. Two big problems with the model are there are no real symbolic abstractions which can be used for reasoning. And if we want guarantees, we really want the model to reason. We want to know why the model has come and decided that this is what you should be doing. We would like the model to explain what it is doing. And for us, mere explanations are not enough. We would want it to give reasons for why it took these decisions, perhaps at different steps, different points. And yet another problem is one of constraint enforcement. I mean, there are certain decisions we don't want the model to take. We don't want the model to spit out certain kinds of advice. Yeah? But it is very hard to guardrail these models to do that. Yeah? So going back to what Kahneman proposed in his, this is something that perhaps, again, all of you are familiar with. So Kahneman is a Nobel laureate, and he thinks of human cognition as two separate systems. System one, which he says system one and system two. System one being fast, automatic, intuitive way of understanding things. It is really based on perception, and it does not really require great amount of reasoning. But on top of that, cognition really involves actually rule-based reasoning, logical checking, verification, which most of us do. And system two also sort of tells us that we have to be analytical. You may perceive things, but after perceiving these things, these objects, you have to analyze what you have seen, and cognition is built out of both these systems, not merely one of just system. And what we believe now is that the models that we saw till 2023 were really models which were good at system 1, perhaps not so good at system 2. So now how do you bring in system 2? And for that, at least the snake oil that is being proposed is symbolic AI. Now, so what is symbolic AI? Symbolic AI is AI rooted in logic. Now, of course, all of us know that coding, modern day computer coding is entirely rooted in logic. And if there were no logic, then perhaps not only would you not see code, you would probably not even have seen a computer actually, because logic goes back to 1850s, 1860s, and it is really the discovery of logic that led to probably Gödel and Turing coming up with their models of computation. Those abstractions also came out of logic, and logic has been at the forefront of machine learning for many, many years. Now, it took a back seat in the last 15 years, and now people want to bring back logic into these models. What logic allows us to do, which I will not spend much time on, is to build not monolith systems, but modular systems, because you can change the piece of logic that you ask your model to work with. Yeah, that is something that logic allows. Okay, so you want to bring in symbolic thinking into models. So these are the paradigms of neuroscience. So when you want to bring it along with the models that are present now, you call that Neuro Symbolic. Yeah? Where you have neural models, but embedded inside these neural models are certain symbolic thinking processes. So you can then you can achieve the following. You can have neural learning with constraints. Then you could learn symbolic rules. You could perceive and also add on top of it a layer of symbolic reasoning. So this is what my talk is going to be today, Neuro Symbolic AI. And if you look at, so this paper sort of lays down very neatly the two broad paradigms of Neuro Symbolic AI, some of which is familiar again to a lot of practitioners. So the first paradigm says, well, you actually integrate symbolic knowledge along with the neural patterns. So these neural patterns are a bunch of weights that you actually see, and what a model uses to finally make its decision. So those are what we call neural patterns, and the first paradigm says, well, you integrate symbolic logic directly into this. The second says, well, from these neural patterns that the model discovers, you extract symbolic representations and you reason with these symbolic representations. Yeah? So there are two realizations for these paradigms. The first realization is you actually use knowledge graph embeddings, and the second is based on extracting out from these neural patterns symbolic representations. So I will just go through examples actually. So knowledge graph embedding is something that, again, which is probably familiar to some of you. So let me just quickly go through an example. So here what we do is, so there is a graph that you have. It's a symbolic knowledge graph. For example, the graph could have triples of the following kind. Here is, an example is that of Paris is the capital of France. So what you do is you take this symbolic, this text that you have, and you embed these texts as vectors. So Paris gets embedded into a vector called Paris. Now capital of goes embedded into a vector called capital of. And then when you add these two vectors, you observe France. So this is what happens in knowledge graph representations. The knowledge graph is embedded into some higher dimensional vector space, and you start reasoning about your knowledge graph using the embeddings of those vectors in that vector space. Yeah, so that is what knowledge graphs do, and this is an example of the first thing there, where you have integrated symbolic knowledge into neural patterns. So because you are going to finally reason in the embedded space, you have actually embedded your entire symbolic knowledge there, and therefore this is an example of that. Of course, there are pros and cons. Here, You can actually scale the knowledge graph. You can actually, this really scales to large graphs because the graph is now immaterial. You can throw away the graph. It's only the embeddings that matter. And then this brings you into the realm of modern day machine learning. Yeah. The cons are, of course, that you can only do approximate reasoning. There are no logical guarantees or proofs. Yeah. So these are some of the problems with reasoning with knowledge graphs, with that kind of approach. So there was an approach which was very popular in the 90s, in 2000s and in early 2000s also, which is to actually take formal logic and actually embed formal logic into neurons. So this is something that was very popular actually. So you directly integrate your entire symbolic logic directly into a neural network. And now the network really behaves like a circuit. So these were called logic tensor networks. Yeah? So there again, what you're doing is you're directly embedding symbolic logic into your neurons. And the neuron now acts as a circuit. And you can also embed constraints into this because your constraints also go into the neural network. And the neural network is then asked to evaluate a certain input and it will give you a certain output. So because the constraints are embedded, you are ensuring that the outputs that the neural network gives you sort of meets those constraints. Yeah, because you embedded all those constraints into your logic and the logic has gone in and fed into the neural network. Yeah, so this allows you to actually embed constraints into your logic. So there is no inference. Directly the input is evaluated and you get an output. Yeah, but of course there is one problem with this. For example, if I have this particular thing which says, well, if X is a human, then X is mortal. And suppose then you have one more rule which says, well, Socrates was human. Then of course, so in this logic, the fact that Socrates is mortal is actually provable. But when you do this embedding, you observe that the probability that the model will tell you that Socrates is the mortal is only 0.87. So although we know this for certainty in this logic, the model will only give you this with probability 0.87. So there are problems with the first approach. So in all these, you have integrated symbolic representations directly with your neurons. So as opposed to that, what you want to do is something different. You want to sort of use symbolic verification along with reasoning. So this is the snake oil that is being proposed. Now, whether it will work, whether it will scale, these are different problems. These are issues which only time will tell whether we will get there. So what you want to do is the following. This is the next slide, sorry. So neuro-symbolic architecture are on the other hand side something slightly different. So you have a neural model. The neural model so there are again two architectures that are popular. And there is a neural model. The neural model proposes the candidate solution. From the candidate solution, you extract out certain symbolic patterns and you ask your symbolic. So now there are a lot of symbolic solvers that are available. You run the symbolic expression that is proposed by your candidate that you get from your candidate solution. You ask your symbolic solver whether it meets the specifications. If it does, then you output it. Otherwise, you don't output it. Yeah? So the neural model has given you a certain solution. You take that solution, embed it into logic, and you run it through a symbolic solver, which will tell you whether you have met your specification. So a good example of this will come in 2 slides. Yeah, so this is one architecture. This is one pipeline that people use. The other is where you use your symbolic verifier to feed back into the neural model. So your neural model proposes a solution. You have a symbolic verifier, which then either comes up with a counterexample or tells you, yes, this is good. And if it is not good, it will provide you a feedback. The neural model will improve on this. Yeah? So now what you have done is, from your outputs, you have produced some symbolic content. Yeah? How you do that is something that I'm going to explain to you later. Yeah? Okay, so a good example of this is probably, so here is an example. So suppose you had an image with a bunch of cubes and you want to know the following. You want to know the following. What do you want to know? How many red cubes are to the left of the sphere? So you can run it, of course, through an image, a vision model. The vision model will identify the first object as a cube, then it identifies another object as being red, and the symbols that this model will produce for you in the output in the first pipeline that I gave you, it is going to take the solution, and from that solution, it is going to produce for you this symbolic expression: cube, red, the object 1 is to the left of object S1, and so on. It is going to produce for you this. Then, of course, you can pass this to a symbolic solver, which is going to tell you, okay, then in the end, that the number of cubes to the left of the sphere is 1, and this output is correct. Yeah? So this is something that can actually be done. Yeah? So another good example of this is of the other paradigm, which is the feedback loop, is synthesizing a program. So how do you do that? Well, the program comes with a specification, and LLM produces for you a program. It produces a candidate proof. A verifier can then check whether the program that has been spit out by the LLM meets the specification or not. And if it does not meet, it will provide you a counterexample. You take this counterexample, feed it back to the LLM, and let this loop run for some time. Yeah, and in the end, the output, it will produce the output only if it passes through the symbolic verifier. Yeah, so this is one paradigm that is again very popular. A big problem with this is one of scaling. How do you integrate reasoning into LLM models at scale? This is really a big problem that needs to be addressed. If you want your outputs to be verifiable, if you want them to be trustworthy, then you would need to scale symbolic reasoning, and that is not very, very easy. But there are good approaches, actually. So what have been the approaches in the past 2 years? In the first, maybe in 2023 to 2024, what people were trying to do was to enhance LLM reasoning itself. Yeah? So how do you enhance LLM reasoning? So via chain of thought, you actually provide the LLM with prompts, and these prompts allow the LLM to sort of generate intermediate reasoning steps, and then you actually use textual reasoning as a proxy for symbolic reasoning. So this was the chain of thought. The way it was done was really prompting the LLM to provide you with intermediate reasoning steps. So this led to this paradigm, this phrase called chain of thought. And the other was to actually explore multiple reasoning directions, tell the LLM to explore multiple reasoning directions, and then provide you reasoning steps along the different paths that it could potentially take. So there were ways that people did it. There was beam search, tree search, and so on. But the big problem with this is that all this is being done during training, but at inference time, the model has to go through this entire process, and of course, this makes your inference extremely time-consuming. There is latency in high inference time. Latency is a natural consequence of the way you have done this. And this is really computationally impractical. So reasoning is encouraged at inference time, but reasoning is not learned in such a process. So there were sort of ways to sort of enhance symbolic reasoning in LLMs. So how was this achieved? What people did was to fine-tune LLMs with formal proof steps. So you take formal logic, you convert it, and use that to fine-tune your models. And you use systems such as Lean. So Lean is a programming language which will allow you to actually generate training data out of logic, actually. And you take this logic to train your model to reason. So while this is very effective for domains such as theorem proving, this proved to be quite useless when it came to real-world tasks. It is very good at theorem proving, very good at certain kind of math problems. So in fact, all the math, so when people tell you that LLMs are good at solving math Olympiad problems, it is because they have been actually trained along with lean. You see, you have used lean in the background to take the problem, translate it into a particular language. Then the solver knows which paths it needs to take in order to get to the output. Yeah? Then there was one more approach where people tried to actually translate natural language directly into symbolic form. Yeah? But again, there were limitations. This is fairly unreliable. You would generate, for real world applications, the symbolic representations generated were reasonably incorrect actually. And of course, it fails on real world problems. So while symbolic reasoning is powerful, it appeared for a very long time that symbolic reasoning is hard to scale, excepting in formal domains like mathematics, certain kinds of mathematics also, and maybe in logic. Okay? So over the last, 6 months or so, there have been some very interesting sort of attempts at scaling symbolic logic. Yeah? So here is, this is the last slide, or the second last slide, I think. So how do you, so far what have we done? We have actually taken this LLM model and we have imposed on the LLM model our kinds of thinking. So what I find very interesting about this particular approach is that now the LLMs, so I'll take about 2 minutes. Yeah, is it okay? 2 minutes? Yeah. So now what we want to do is to take these LLMs and train them with not the way we think, but the way LLMs actually think. Yeah? So this is quite interesting because admittedly, none of us know how LLMs think. Now, by asking LLMs to think the way we are thinking and then produce traces of reasoning is probably not the right way to do it. So what seems reasonable is to say, well, if you were an LLM, how would you have thought? So this is what they actually do. They try to steer LLMs to generate reasoning trajectories, and these reasoning trajectories will be provided to you in some symbolic formalism. But how do you get these trajectories? That's point number 2 here. These reasoning trajectories, so suppose you want to train a small LLM for something. You use a larger LLM, you tell the larger LLM, look, I want you to reason about this. What would be the reasoning steps you would provide? You use those reasoning steps, you use it in a Monte Carlo fashion, yeah, and generate sort of labels of reasoning patterns and are they good or bad. Generate sort of supervised labels of reasoning patterns of a larger LLM. Then you train a model to sort of output really good reasoning trajectories. Use that to fine-tune your smaller LLM. Yeah? So this is the approach that people are trying. This has, at least in certain cases, people have shown that this really scales well. Because now you're not dealing with sort of artificially introducing certain kinds of ways of asking the model to respond. The model is now responding the way it would have responded had it been. So in some sense, this goes back to the talk of yesterday. A father LLM is really being used to extract out reasoning strategies. And now the father LLM's reasoning strategies are being put into the smaller LLM. Yeah? So these are, and the outcomes, there are good outcomes, I think. Yeah? So this seems to be something that people are pursuing. Yeah? Okay. Of course, these are applications that we are interested in. Yeah? And anyway, I think I missed a slide. I missed a slide, I think. Okay. So the takeaway from this is that, well, so far we were looking at sort of AI, and maybe the road forward is Neuro Symbolic AI, where you sort of train these models to reason. But what exactly is the training? Probably, I certainly believe that training an LLM to reason the way it would reason is probably the right way. Just like when we train our child to reason in a particular way, we train the child to reason in the way we reason. Yeah? So probably this is a scalable version of reasoning. I believe so, but only time will tell us whether that is actually true. Yeah? So I'll stop with this.
Thank you, sir. Thank you so much for a very nice session. May we request Mr. Sukumar, sir, to join us on stage and present a memento to Professor as a token of gratitude.